Now, when we report GPS accuracy, there are a variety of different statistical methods used to calculate that accuracy. Different manufacturers will use different types of GPS calculations or accuracy calculations in order to provide information that's included in marketing documents and brochures. The key point is to understand what type of accuracy calculation was used and what type of accuracy the term is relating to in order to be able to truly compare these systems. Some examples include things like CEP, RMS, and 2D RMS. And again, each of these statistical accuracy measurements can be made for both static or dynamic accuracy, or pass-to-pass accuracy in that case. So they will link with the type of accuracy measurement or type of accuracy test conducted. So the key point is that we understand both the type of accuracy that's being discussed and the statistical method used to report that accuracy. So let's talk a little bit about the comparison of accuracy versus precision. And this somewhat gets back into our discussion of pass-to-pass versus long-term accuracy, year-to-year accuracy. The photo on the left, or the image on the left, shows a targeted bullseye with a scatter of points along that target. Now, if we look at this, we would say, well, the overall performance, if that's a GPS receiver, is accurate, because if we average those points, we'll end up with a location that's located in the center. We would say, though, that's not very precise, because there's actually quite a bit of scatter or point change across that target. So this type of application really doesn't fit many precision ag applications very well. The precision, or this close clustering of points, is what we're really after in precision ag applications. So the photo in the middle, the image in the middle, shows a tight cluster of points, although it's not in the center of the target. So we would say this receiver is not overly accurate as far as giving us the exact location, but it's very precise. Each individual measurement point is going to be rather close to the actual value, or to the last measurement point. And so this receiver would exhibit a high quality of what we call pass-to-pass accuracy. The precision on the far, or the receiver or image on the far right, would represent RTK level accuracy, in which we're not only very precise and tightly clustered, but also very accurate in the overall signal performance, meaning we have very low deviation from the 0 point of our system. When we measure this accuracy, there's typically two calculations or statistical metrics that we're looking at. First being the mean, or the average location. The second being the standard deviation, or how much variability we have in that average location. Now, when we talk about measuring a GPS accuracy, we're talking total error, but we really have error in the x direction or easting, as well as error in the northing direction. And you notice that I'm talking in terms of easting and northing, which are projected units, rather than latitude and longitude. That, of course, is because latitude and longitude don't have any actual relation to a distance or a displacement of error. So we do have to project data into a local coordinate system in order to statistically analyze it. Now, a quick reminder of some statistical lessons. If we have a set of data, like GPS error, and it's normally distributed around some mean, then we would expect that from that mean, if we offset ourselves one standard deviation positive or one standard deviation negative, that we should have 68% of the data points lie within that range. Likewise, if we have 2 sigma, 2 standard deviations, plus or minus, then we would expect 95% of the data points to lie within that range. 3 standard deviations is going to include up to 99% of those data points. Now, why is this important? depending on how we calculate or what statistical level we use, whether you use 1 sigma or 2 sigma, 1 standard deviation or 2 standard deviations, will influence the overall accuracy, or excuse me, not the accuracy, but the overall magnitude of the accuracy number. We can also take that error and simply make a scatter plot of it, and you can imagine that we could draw in a circle here in the center that would include 68% of our points, and that circle would be the distance, the radius of that circle would be our 1 sigma error level for that receiver. This same data set could also have a circle which includes 95% of the points, which would have a radius virtually twice as large as our 68% signal. So the same data set can result in two very different accuracy or performance values. Knowing that we can have multiple values come out of a single set of data is a strong indicator for why we have to be clear about what type of accuracy metric we're using to evaluate our GPS data to begin with. To calculate the 1D accuracy of a GPS receiver, what we really need to find is the 1 sigma accuracy level. And the 1 sigma total is equal to the sigma squared, or the standard deviation squared in the x direction, easting, plus the standard deviation squared of the y direction, northing. We square the two standard deviations, add them together, take the square root of that, and it gives us a resulting total or overall sigma value, or standard deviation. That standard deviation is a direct representation of the root mean square error for the GPS receiver. So when you see an RMS error, root mean squared error, that's giving you the 1 sigma, or the 68% accuracy calculation. The circular error probability, or CEP, gives us essentially a 50% probability rather than the 68% talked about previously. This is calculated as 0.589 times our standard deviation x plus standard deviation y. This is really fairly not used very often, but is occasionally seen on GPS specifications. 2D RMS is the most common type of GPS measurement in typical precision ag systems. This represents 95% of the points, or has a 95% probability will be within this error. So 95% of our points would be inside our error circle. The radius of that circle is our 2 sigma level, and this is simply calculated as 2 times our original sigma measurement, which is standard deviation of x squared plus standard deviation of y squared, all taken to the square root. Again, our x data is going to come, x and y data is going to come from projections of latitude and longitude into easting and northing coordinates. Here's another graphical comparison of how the same set of data can be represented with two different metrics. This is data provided by Novotel for one of their GPS receivers. The red line indicates the 50% CEP accuracy of 1.8 meters. The magenta or light purple line shows the RMS accuracy of 2.16 meters. And so if we're comparing two receivers, it's critical to understand what is the accuracy value used in order to be able to compare the performance of two different units. If you have GPS receivers in different values, we can cross-convert between the two by using this table, which relates the value of CEP, 50% probability, to RMS and to 2D RMS. Now remember that although this allows us to convert the measurement statistic, the value itself, we still have to have data that is compared into the same type of test. So if we have static accuracy data in two different reporting methods, we can convert those so they can be compared. But if we have static accuracy from one receiver and dynamic accuracy from another receiver, we really have no way to compare those two metrics. When 3D accuracy measurement is required, we typically use spherical error probability, which is SEP for short. This is calculated as 0.513 times the summation of our standard deviations in x, y, and z. And this will give us a probability of 50% of the positions being within this sphere of error, or this three-dimensional error characteristic. Let's take a look at how different manufacturers will report this error. Each of these four images is just a screenshot from different manufacturer websites. On the top left, you notice that under the static accuracy, we're given simply sub-meter differential accuracy. Pass-to-pass accuracy, though, is rated as 4 to 12 inches, and that would be for a WASP-based correction. The one on the right shows simply position accuracy of sub-meter, does not even break it into pass-to-pass or static. We would assume that to be static accuracy. The one on the left, on the bottom left and the bottom right, show the accuracy broken into different levels. If we have only GPS accuracy, we would expect less than 15 meters of 95%, or 2D RMS. If we use WAS, we should have less than 3 meters 2D RMS, and this will be for a small handheld GPS receiver. Here's a similar table provided by Trimble. This shows a couple of their different receivers and has different levels of GPS accuracy depending on the correction. Their AgGPS 106, which is just a generic integrated antenna receiver for general purpose operations, indicates a less than 2 to 3 meter DGPS WASP-based accuracy. The AgGPS 252 receiver shows different levels of accuracy, as do the 333 receivers, depending on the type of solution. In this case, we have OmniStar XP at less than 20 centimeters, OmniStar HP at less than 10 centimeters, and RTK at less than 1 centimeter. When not listed, we assume these to be static 24-hour accuracies. The same type of accuracy measurements can come out in press releases on different receivers as well. This happens to be from a software update released for the Starfire Deer receiver a few years ago now. But you'll notice one of the things they mention is that on their long-range RTK, they're now approved for 12-mile line of sight 68% of the time. 68% tells you they're using 1 sigma or 1D RMS accuracy as their accuracy metric. Here's an example comparison of a single receiver that may have a specification of 1.2 feet RMS, 2.4 feet 2D RMS, or 1 foot CEP. In this case, each of these values is actually the same value, or the same overall accuracy. So let's quickly walk through how we would actually calculate accuracy in a practical application. If we have a set of data, and this could be in Excel, where we have the X or easting value, the northing value Y, for a variety of points, we end up with a table of easting and northing values. If we calculate the mean and the standard deviation of those data sets, then directly from the standard deviation we can calculate the RMS, 2D RMS, and CEP precision or overall accuracy. It should be noted that the units of our accuracy measurement are the same as the units used for northing and easting values.